Imagine trying to predict whether a city's power grid will overload next week. If you feed a model only the last month's load data, you're essentially fitting a curve to noise. But introduce a forecasted heat wave, or a new industrial plant coming online, and the trajectory shifts entirely. That's the core limitation of traditional time series forecasting. Real-world systems aren't just autoregressive. They're driven by exogenous shocks, policy shifts, and market dynamics. To capture this, researchers have been pushing context-aided forecasting, where language models ingest unstructured text alongside numerical time series. The problem? Almost every benchmark hands the model the relevant context on a silver platter. In production, an AI doesn't get curated datasets. It has to retrieve, filter, and synthesize signal from thousands of noisy, contradictory documents. That gap is exactly what Dr-CiK was built to measure. It's a benchmark designed to stress test whether AI agents can actively discover, validate, and integrate forecasting-relevant context. The testbed spans energy, transportation, healthcare, and finance, but the real innovation is in its distractor design. These aren't random off-topic articles. They're structurally adversarial. A document might reference the exact same asset and event, but place it in the wrong temporal window, or describe a plausible but confounding causal factor. Solving these tasks requires multi-hop reasoning, cross-referencing timestamps, aligning numerical baselines, and explicitly filtering out high-similarity noise. So how do current systems actually handle this? The results are stark. When models are fed ground truth context, forecasting accuracy jumps significantly. But when we hand state-of-the-art research agents the raw document pool and ask them to find that context, they falter. Most recover less than 5% of the actual supporting evidence. Worse, over 80% of their citations land on those carefully engineered distractors. In many cases, feeding the agent's own retrieved context into the forecasting head actually degrades performance below baseline historical models. The bottleneck isn't the time series predictor. It's the retrieval and reasoning pipeline. Current architectures rely heavily on dense vector retrieval and semantic matching. They're excellent at surface-level topic alignment, but brittle when temporal and causal reasoning are required. Agents frequently misalign timestamps, truncate critical numerical ranges during summarization, or get trapped by documents that sound authoritative but contradict the actual trend. Even when the right documents surface, the agent often fails to distill them into actionable features. The system isn't broken, it's just optimizing for the wrong objective. It's retrieving information, not evaluating predictive utility. And that brings us to the second, more subtle failure mode, specificity collapse. Imagine handing an AI maintenance logs, safety reports, and shift schedules, then asking it to forecast system behavior. The agent successfully ignores red herrings, follows multi-step causal chains, and retrieves the correct documents. But when it synthesizes the output, something degrades. The precise numbers evaporate. A shift change from 6 to midnight becomes a vague, renovation and heavy labor phase. 169 low-usage instances becomes wattage reductions. A firm operational state, like permanent, gets softened into steady upward momentum. Why does this happen? It's baked into the model's training objectives. Large language models are optimized to minimize perplexity and maximize fluency, heavily reinforced by reinforcement learning from human feedback to sound like polished analysts rather than technical transcribers. Quoting exact timestamps, counts, and operational states feels too rigid, so the model paraphrases. Tokenization also plays a role. Precise numerical strings often get fragmented or mapped to less frequent tokens, pushing the decoder toward higher probability, more generic phrasing. This isn't a retrieval failure. It's a synthesis failure. The system found the signal, but traded precision for narrative coherence. You might dismiss this as a stylistic quirk. For forecasting models, it's catastrophic. Predictive architectures rely on exact temporal anchors to align exogenous variables, split training windows, and detect regime changes. When an AI replaces a precise timestamp with a vague phase, it strips away the coordinates the forecasting head needs to weight external features correctly. The benchmark data confirms this. While high-quality context helps, synthesizing it into summaries only partially closes the performance gap. Some models actually ignore the text entirely, reverting to raw historical data because the synthesized context lacks the numerical fidelity required for reliable inference. What does this tell us about the state of AI forecasting? We've largely solved surface-level retrieval and multi-step logic. But we're hitting a wall at precision-preserving synthesis. The next frontier isn't just bigger models or broader knowledge bases. It's architectures that treat numerical and temporal specificity as first-class citizens, not optional details. We need agents that don't just search and summarize, but actively evaluate the predictive utility of every token they extract. Dr-CiK doesn't just expose a gap in current systems. It maps out exactly what we need to build next. AI that doesn't just react to the past, but genuinely reasons about the external forces shaping what comes next.